These are your notes for Unit 13, Day 1 of Pre-Calculus. If you would like to see the warm-up, our review question, or any homework or test questions we went over in class today, just look at your finished notes. So today we're going to talk about the foundations of probability. We're going to begin by talking about sets and subsets, and so we'll get into what a set looks like, what the proper notation is. We'll talk about Venn diagrams and how we can use those to talk about sets. We will talk about the fundamental counting principle and how we can use that to solve some problems that maybe you did in grade school that took you a long time. And then we'll talk about things called permutations and combinations, which allow us to find how many different ways we can arrange people into groups, or how we can arrange people into like a first, second, and third place. And again, those are called permutations and combinations. So let's start with sets and set notation. So let's say we start with just set A, and set A contains the elements 1, 2, and 3. And typically we put sets in those braces, which I call birdie brackets. And then let's say we have set B, which is also the elements 1, 2, and 3. Now notice those two sets are identical. If two sets contain the exact same elements, then we can say they're equal to. So set A is equal to set B. If you have two sets, and let's say set A is the elements A and B, and then let's say set B is the elements A, B, C, D, and E. Now notice they're not equivalent, but all of the elements in A, which are just A and B, are also contained in B. If the elements of one set are contained in another set, then we call that set a subset of the other set. So A is a subset of B. And the symbol we use for the subset, it's a elongated C with a bar underneath it. And I usually say A is contained in B, but I think the actual way we're supposed to say it is A is a subset of B. Now, if A is a subset of B and it's not exactly B, so up here we had A is 1, 2, 3 and B is 1, 2, 3. A is technically a subset of B because all of the elements of A are in B as well, but it's not a proper subset. A proper subset are when all of the elements are in the other set, but it's not the set itself. And so if you want to do a proper subset, you would just do C without the bar underneath. So it's kind of like greater than or equal to or just greater than. So this, with the elongated C without the bar underneath, that means it's a proper subset, meaning that it has the elements, all of the elements of A are in B, but it's not B itself. So A is not equal to B. And then we can call it a proper subset. All right. And then we have something called the empty set. So we could call set C the empty set, and we do the empty set with empty birdie brackets, or you could do it with the big O with the bar through it. The empty subset is a subset of every set. So C is going to be a subset of A, and C is going to be a proper subset of B. The empty set is a subset of every set. All right, so in our example, write down all the subsets of set A, B, C. All right, so all the subsets. So we could have set A, B, C, just as individual elements. Those would be proper subsets of the set ABC. And we could do it with two elements, so AB, BC, and AC. Sorry, my birdie brackets are terrible when I'm going fast. And then we could do all three, A, B, C. And then we could also have the empty set. So how many subsets are there? There's 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 subsets of the set ABC. If we wanted to know how many subsets there would be from the start, there is a pattern to this. It's 2 raised to the number of elements. So notice there are 3 elements in my original set. So if I want to know how many subsets it would be 2 raised to the number of elements. So 2 to the third is 8, and notice we got 8 subsets. So if you want to know how many subsets a set would have, you count up how many elements it has, and then you do 2 raised to the number of elements, and that is going to be the number of subsets that set would have. All right. As I stated before, we can use Venn diagrams to analyze a data set. So in a survey of 100 college students, 35 were registered in college algebra, 52 were registered in Computer Science 1, and 18 were registered in both courses. So when I do Venn diagrams, I put them in a box, and the box represents all of the possible students. So all of the possible students was 100. So there should be 100 total students within my box. And now we have two sets. So if you guys remember, Venn diagrams are made by circles. So we have Venn diagram with two circles because there's going to be two different things. And so we have computer science is going to be one of my circles. So computer science 1. And then my other circle are going to be all of the students in college algebra. If they have elements in common, those people in common would go in the middle. So this would be people in both computer science 1 and college algebra. Well, we know that there's 18 people taking both courses. So now we've kind of just got to look. So 52 total people are in college algebra. So in my red circle, I need 52 total people. Well, 18 of them are already in the middle. So the rest of them is going to be 52 minus 18, which is going to be 34. So altogether, I should have 52 people in college algebra. So if I take 34 plus 18, then I get my 52 people in college algebra. And then I need, that's going to be for computer science. So this is going to be 34 and 18 in computer science. And then so 52 were in computer science. 35 were in college algebra. So I know that in college algebra, there's 18 that are in both. There's 35 total in college algebra. So I need the 17 other people, because if I did 35 minus 18, I'd get 17. So all together, I have 18 people that are taking both college algebra and computer science. I have 17 people who are just taking college algebra, and I have 34 people who are just taking computer science. All right, so how many students were registered in college algebra or computer science? Well, we've already answered that. There's 17 just in college algebra, and then there's 34 just in computer science. How many were registered in neither course? Well, in neither course would be on the outside of both circles. So neither would be represented on the outside. Well, I know there's 100 total college students that were surveyed. And so if I took 17 plus 18 plus 34, I would get 35 plus 34. So I'd get 69. So I know that there's 69 students that are enrolled in one of the courses. So if I took 100 minus 69, I'm going to get 31. So there's 31 students that are not enrolled in either course. So there's 100 students, there's 100 students total, and then there's going to be 31 students that are not enrolled in either course. So there's 100 students total, 31 are not enrolled in either course. All right. Table 1 lists the level of education for all U.S. residents 25 of age or older in 2017. So how many U.S. residents 25 or older had an associate's degree or a bachelor's degree? So you would just add these two columns together, and we would get 0, 0, 0, 2, 7, 5, 8. So 68,572,000 had an associate's or bachelor's degree that were 25 or older in 2017. So how many U.S. residents 25 years of age or older had an associate's degree, a bachelor's degree, or an advanced degree? So now I'm going to take the 27,841,000 and add it to what I just got. So 0, 0, 0, and then 3 and 11 and 14 and 16 and 9. So 96,413,000. I'm sure you guys can all read a table and answer those questions. All right. So one of the foundational skills in probability is called the fundamental counting principle. So when you guys did the warm-up and you wanted to know how many different ways there are to arrange the letters in the word Jupiter, you could have used the fundamental counting principle to make your life way easier to do that problem. So a fixed price dinner at McKenna Restaurant provides the following choices. You can have a soup or a salad for an appetizer. You can have baked chicken, broiled beef patty, beef liver, or roast beef au jus for your entree. Or you can have ice cream or cheesecake for dessert. How many different meals can be ordered? Well, the good news is you don't have to list out, like, if you ordered a soup and a baked chicken and an ice cream, or if you ordered a salad and a baked chicken or an ice cream. You don't have to go through like your different trees. You might have made trees when you were in grade school or things like that. You don't have to go through this. So the fundamental counting principle says that if you had n elements, then the different ways to arrange them is going to be n factorial. So you have n factorial different ways to arrange them. And what is n factorial? I think we talked about this at some point this year. So n factorial would be n times n minus 1 times n minus 2 times da, 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 and then you get all the way down. So if you had something like 5 factorial, it would be 5 times 4 times 3 times 2 times 1. And you can literally multiply that out. Or you have a button on your calculator that can do it for you. So typically you have a math button. If you have a TI-83 or TI-80, anything, you hit the math button and then go over to probability. And then you have a factorial button. And then you have other buttons that we're going to use today. You have like the NPR, the NPR and the NCR buttons. We're going to use all of those today. If you have a scientific calculator, you might have to find those buttons. I think we tried to find them for most of you guys at some point a few classes ago. You also have them on Desmos, and I'll show you how to do these on Desmos in a second. So how many different options do I have? So I have a soup or a salad, so that's 2 options. Baked potato, broiled beef patty, beef liver, or beef au jus. So 1, 2, 3, that's 4 options. And then ice cream or cheesecake, that's 2 options. So I can choose 2 times 4 times 2 different options. So how many different meals could be ordered? There'd be 2 times 4 times 2 different ways of doing it. So there's 16 different meals that I could order. Or you could do like soup, salad, right? And then from the soup or salad, you have 4 options, 2, 3, 4, 1, 2, 3, 4. And then from those 4, you've got the 2 desserts. I don't know if you guys made these trees in grade school. And so you would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 if you made the tree. Or if you listed them all out one at a time, you would have 16 different options. Oh, sorry. This is not how you do those. Sorry. You just multiply all the different options. So if you had like, the fundamental counting principle is not the factorial button. It's you just multiply all of the options together. So multiply all the total options. We're going to use factorials in a second. Sorry about that. So you're going to multiply all of the total options. Factorials and the NCR and NPR are going to be used in a second. I got ahead of myself. I apologize. All right. So the International Airline Transportation Association assigns 3-letter codes to represent airport locations. For example, Fort Lauderdale in Florida is represented by FLL. Notice that repetition is allowed in forming this code. How many different airport codes are possible? Okay, well, you have 3 different letters that you're choosing. How many letters are there in the alphabet? Well, there's 26 letters in the alphabet. And you can repeat. So how many options are there? Well, you just get to multiply all of your options. So you're going to take 26 options for the first one. So you could pick A, B, C, D, all the way through the Z for the first option. And then for the second option, again, you could take A, B, C, D, all the way to Z. Those could be your second option. And the same for the third. So all of the options would be 26 times 26 times 26. I'm sure that there's actually some options that wouldn't work based on what those letters would spell out. But there's going to be 17,576 different options for those 3-letter airport codes. Where does the fundamental counting principle come into play a lot is with passwords. So why do people say that having a longer password is better than having like a strange password? Well, the longer your password is, the more options you have. So let's look at how many 2-symbol code words can be formed if the first symbol is an uppercase letter, and the second symbol is a digit. All right, so we have two things. The first one is going to be an uppercase letter. So you have 26 options for an uppercase letter. And then a digit. Well, your digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. A digit is one number. So you have 10 different digits if you count all of those. So how many different passcodes could you have? Would be 260. Now, if we think about it, if you did like a 7-letter password, so 1, 2, 3, 4, 5, 6, 7, and you only did numbers or letters, well, there's 26 letters, right? But you could do upper or lowercase. So altogether, there's 52 different letters that you could choose from. And then for numbers, well, it's the digits. So for numbers, you have 10 different numbers. And then for symbols, I don't actually know how many different symbols there are. Well, let's just say that there's 20 different symbols you could choose from. Well, then for every single option for each of these, if you had a password that's 7 items long, then you have 52 plus 10 plus 20 different options for each of those symbols. So 62. So you would have 82 options for each part of your password. And so if we did that, it would be 82 to the 7th power. And so that's how many options you would have. But let's just say we made our password 8 letters or symbols long instead of 7. So notice we have 2.49 times 10 to the 13th. If I made that up to 8, notice I have 2.044 times 10 to the 15th. So I made this bigger by a factor of 100 times bigger. Or if I did it times 9, if I made my password 9 as long. So every time you're making it 100 times bigger than what the original one was. Or you have 100 times more options than you did. So the longer the password, the more safe and secure you are. Okay, so that's the fundamental counting principle. You just get to multiply how many different options you had for each idea. So now we're going to get more specific. Permutations, and this is where factorials are going to come into play. So permutations are the different ways that you can arrange items or people or anything that you're talking about in a specific order. So for permutations, you're talking about a specific order. So like first place, second place, or third place. Or you're talking about specific positions like a president, vice president, and secretary. So you're not forming a group, you're forming specific things. So a first place, a second place, and a third place. Or a president, vice president, and secretary. Or you're forming specific positions on a team, like a forward, a defender, and a midfield. So how do you figure out how many different ways there are to do this from a group of people? So let's say that there's 10,000 people running a race. And you want to know how many different ways can you get a first place, a second place, and a third place finisher. There's a formula, and we'll talk about the formula, but there's also a way just to think through it. Well, how many different options do you have for somebody to finish in first place? Well, 10,000 different people could finish in first place. And then somebody finished in first place. So how many options do you have for somebody to finish in second place? Well, now you have 9,999 options for somebody to finish in second place because somebody already finished in first place. And then for your third place finisher, you have 9,998 options. So that's how many different ways somebody could finish first, second, and third place if 10,000 people were running a race. Or on your calculator, this ends up being 10,000 factorial over 10,000 minus 3 factorial. That's what this ends up becoming. So 10,000 factorial means 10,000 times 9,999 times 9,998 times 10,996, all the way down to 1. And then 1,000 minus 3 would be 9,997, and then all the way down to 1. And notice the only 3 that are left after you cancel will be 10,000, 9,999, and 9,998. And so I'm going to do this both ways on Desmos. And so if I took 10,000 times 9,999 times 9,998, that's how many different options I would get. So 9.9970002 times 10 to the 11th power. That's a lot of options. On Desmos, if you're going to do NPR, or like a permutation, you hit functions, and then you're going to go to stats, and then notice down here you have the NPR and NCR. So I'm going to do NPR, and then you just want to do what we're doing. We're going to do, in this problem, it would be NPR, and then we're going to do 10,000, and then we're going to select 3 people from that. So 10,000 and then comma 3. And notice it's the exact same answer from up above when we just multiplied it out. So this is 9.9970002 times 10 to the 11th power. So I could move that decimal point 11 places to the right, and that's how many different ways somebody could finish first, second, and third place from that race. Again, if you were going to do this on your calculator, if you have a TI, you hit the math button and then hit the probability button. So go over to probability. And then if you're using a TI, you're actually going to have to do the first number first. So you're going to do 10,000 first and then do those steps. So then hit math, probability, go over to NPR. And then after you do that, you would hit the number 3 and then hit enter, and then it would give you your answer. I'm assuming that's how it'll work on even the scientific calculator. So start by hitting 10,000, then hit the NPR button, and then hit 3. And then it should give you those options. All right, so let's do these examples. So in A, it said P. So this NPR is going to be 7P3, or you could do P and then 7, 3 in parentheses. They mean the exact same thing. And so this would be 7 factorial over 7 minus 3 factorial. Or you're going to do 3 positions, and you had 7, then 6, then 5. You could do it either way. And so this is going to be 42 times 5. And so you get 210. Or if you did it with the functions button on your calculator, you would do 7, 3. And you get 210. So notice you get the same thing. And then how many different ways out of a group of 6 people could somebody finish first? Well, obviously that's going to be 6. If you had 52 people, how many ways could somebody finish first, second, third, fourth, and fifth? That's what that part C is going to do. And this one says it's calculator problem. So we'll do our calculator, and then we're going to do 52, and we want 5 different places. And so this is going to be 3. So it's going to be 311,875,200. And those are permutations. So let's look at an example. All we know about Shannon, Patrick, and Ryan is that they have different birthdays. If all the possible ways this can occur were listed, how many different ways could there be? Assume that there's 365 days in a year. Okay, well, there's 365 days, and we want to choose 3 different ways. So it's kind of like day 1, day 2, day 3, but they all have to be different. So that's what we're going to do. Or we're going to do 365 times 364 times 363. Either way that you do, it's okay. And so if I do this, I'm going to just erase those. And I'm going to do 365, and I want 3 different days. And so there are 48,228,180 different ways that they could have 3 different birthdays. All right, so combinations. Combinations are different than permutations because instead of choosing a specific order, you're choosing a group. So like a committee or a team. So if like 200 people tried out for the basketball team and only 10 people made the cut, then how many different ways could those 10 people be selected? So again, it's not specific positions this time. It's a group or a committee or a team. So you don't care what order they're selected in. You just want to pick 5 people out of 300 people or something like that. Those are combinations. And the formula is going to be a little bit different this time. So instead of being able to do it by hand, the calculator is going to be a lot more user-friendly like this. So let's say 200 people try it out, and 10 people made the cut. So this time it's going to be 200, choose 10. So when it's the C, I like to say choose, or you could do C and then 200 and then 10. So the formula this time is you take the total number, so 200, and then you divide by, kind of similar to permutations, so 200 minus 10 factorial, and then times 10 factorial. So there's an extra step, so that number of people that you're choosing gets listed twice, so it's going to be 10 factorial. And so yes, you could do that the long way, or you could just use the NCR button this time. So functions and then NCR, and then it's going to be 200, and we're choosing 10 people from the 200. And notice there's a ton of different ways that this could happen. So the number of ways that those people could be selected for the team would be 2.245100439 times 10 to the 16th power. So there's a ton of different ways that 10 people could be selected to form a team of 10 from 200 people. All right, so let's use our calculator to figure out the rest of them. So 3 choose 1 would be 3 factorial over 3 minus 1 factorial times 1 factorial. So this is going to be 3, but we can use our calculator to check. It's going to be 3 choose 1. So there's 3 different ways of doing this. The next one is 6 choose 3. So how many different ways from 6 people could you choose a group of 3? So this one would be 6 factorial over 6 minus 3 factorial, 3 factorial. Or if we did this, 6 choose 3. And there's 20 different ways of doing that. And then n choose n would be n factorial over n minus n factorial, which is going to be 1. So how many different ways can you choose a group of n people from n people? There's only going to be one way. So if 5 people tried out for the team and 5 people are going to make it, there's only one way to do that. N choose 0. So if we just did like 3 choose 0, it's going to be 0. There's only going to be one way to choose a team of 0 from n people. And then the big one, 52 choose 5, is going to be 2,598,960. And those are combinations. So let's look at an example or two. How many different committees of 3 people can be formed from a group of 7 people? So a committee is a grouping. So it's going to be 7 choose 3, or C 7 comma 3. And so this would be 7 factorial over 7 minus 3 factorial times 3 factorial. And so we can use our calculator again. And so this is going to be 7 comma 3. And there's 35 different ways of choosing a committee of 3 people from 7 people. How many different ways can a committee consisting of 2 faculty members and 3 students be formed if there are 6 faculty members and 10 students that are eligible to serve on the committee? Well, we got to do the faculty members with the faculty members. So we're choosing 2 faculty members from 6. So 6 choose 2. And then it's the fundamental counting principle. So now we're going to multiply in between. Now it's my students. I have 10 total students, and I'm choosing 3 of them. So it'll be 6 choose 2 times 10 choose 3. And again, we can just use our calculator to do this. So 6 choose 2. And then end the parentheses times. And now we're going to do 10 choose 3. And there are 1,800 different ways to form that committee. All right. Now, permutations with repetition. So if we wanted to know how many different ways there are to arrange the letters in like the word rearrange, well, you start with how many letters there are. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 different letters, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. If all the letters were different, then you could do 9 times 8 times 7, times 6 times 5 times 4 times 3 times 2 times 1. That's if all the letters were different. But notice, not all the letters are different. E is up there twice, R is up there twice, and A is up there twice. So if there are repeated elements in your situation, you've got a new one. So you're going to do 9 factorial, because there's 9 different letters, but then every time something's repeated, so notice E happens twice, so I'm going to divide by 2 factorial, which represents the E's that are repeated. R is repeated twice, so I've got a 2 factorial for the R's, and then A is repeated twice. R is repeated 3 times. It'd be helpful if I could count. So E is repeated twice. R is repeated 3 times, so that's going to be 3 factorial. And then A is repeated twice. And then that's it. So now we're going to have a 2 factorial for the A's. And that is going to give me all the different ways of rearranging the letters in the word rearrange. And so if I did that, I would have 9. And then if you go to functions and stats, miscellaneous. Oh, no, I think it's in the normal keyboard actually, isn't it? ABC. Yep, exclamation point. So 9 factorial and then divided by 2 factorial, 3 factorial, and then 2 factorial. And there we go. So there's 15,120 different ways of rearranging the letters in the word rearrange. In the warm-up, we did the word Jupiter. Notice Jupiter doesn't have any repeats. So how many different ways could you rearrange the letters in the word Jupiter? 1, 2, 3, 4, 5, 6, 7. It would be 7 factorial. So hopefully we didn't spend a whole lot of time trying to think of all those. It would have 5,040 different ways of rearranging the letters in the word Jupiter. All right, your homework is 13.1 and 13.2. Let me know if